Hello, students. Welcome back, ladies and gentlemen, to another topic in science. And this week in science, we are going to be exploring atomic bonding. So let's get to it in our books. Make sure your books are out and open and ready to jot down some notes for this week's topic, atomic bonding. So let's go over some general information first, and that is not one of them. Let's go over some general information first, such as you may recall this from when we discussed atoms a couple topics back, and we learned about John Dalton and his atomic theory of matter. Remember the 4 points of the atomic theory of matter. Well, one of those main points was what we're reviewing here right now, that it is the atoms of elements themselves that combine to form new substances. If you need to go back to that previous topic to refresh your memory on some of the details on that, feel free. But this diagram sums it up a little bit. Here we see some atoms of hydrogen, some atoms of oxygen, and keep in mind, these are just diagrams. This is not what the atoms really look like, okay? But it is the atoms themselves which come together to form new substances, and in this case, we've got molecules now of H2O, water, H2O, water. From hydrogen and oxygen, we get water. But it's the atoms themselves of those elements that are actually doing the combining to form the new substances. Next. The whole process of bonding, the whole idea of this week's topic, is determined by atomic structure. And if there's one point in chemistry that you really need to reinforce into your brain, it's this. The particular structure of atoms that's responsible for the bonding are the electrons. We are going to be spending a lot of time this week as we are discussing atomic bonding. We're going to spend a lot of time with the electrons, because it is, as we will discover, the electrons that determine whether or not some element is going to react to another element. We discussed that a little bit last week when we were learning about the periodic table of elements, and we went from the alkali metals on one end over to the noble gases on the other end. And the major reason why the alkali metals were so reactive is because of their valence electrons. They're very unhappy, you might say, or unstable. Whereas the noble gases, their outer energy level is complete with their valence electrons, and they are quite content to be by themselves, which is why they are inert, or they don't chemically react with other substances. The reason for this all is going to come into play here this week as we explore atomic bonding specifically, and we dive into the details of why that does or does not take place. And again, it has to do with the electrons, which, by way of reminder, if you recall the different atomic models that we discussed earlier in the year, electrons are found in the area called the electron cloud. Inside the nucleus, we have the positively charged particles, the protons and the neutrons. But for our purposes here this week, the area we are focusing on is the electron cloud around the nucleus, where the negatively charged electrons can be found. is these electrons which offer the key in chemistry as to what will bond with what and how they go about doing that. So let's explore this a little bit further. If you think of the Niels Bohr model, I mentioned to you at that time that that model would become useful to us, and here's where it becomes useful. We want to think in terms of energy levels. At that time, we discussed how Niels Bohr suggested that the electrons orbit around the nucleus in orbitals like planets orbiting the sun. We are referring to those orbitals as the various energy levels around the nucleus. So around the nucleus, where the positively charged protons and the neutral neutrons are located, we have the first energy level, around which is the second energy level, and there are energy levels beyond that as well, as we will see in just a little while. And I wanted to reinforce the analogy that I gave you when we were talking about this earlier, as far as like a sporting stadium and the seats closer to the nucleus as we advance farther out from the nucleus are like different layers in the stadium. Again, we'll get to that in just a little while. But before we do, I want to talk about what we call neutral atoms. This is really important. You see, when you look at the periodic table, which we learned about last week, and you look at any of those element squares, and you see the symbols for the various elements of the 118 known elements in the universe, the elements that are represented on the periodic table are neutral atoms. Well, what exactly does that mean? What does it mean to be neutral? Well, maybe you've learned about political ideologies in social studies class this year, learning about civics, and you've learned about the right and you've learned about the left, and how there are extreme views on both sides of the political spectrum, and in the middle, you have more moderate views, those that tend to agree with components of both sides or neither side. Well, in a similar way, atoms generally tend to be neutral. They're like moderates in the middle. Neutral atoms have a balanced number of protons and electrons naturally. Now, we're going to see how that changes and how those changes affect the reactivity of elements on the periodic table. Kind of like how politics can cause folks to react one way or another based on particular ideologies. But let's stick with elements in science class here. So imagine a balance or a scale. Here we have a double pan balance. If we put positives on one side and negatives on the other side, as long as you have the same number of positives and the same number of negatives on both sides, then our balance will be balanced. It won't tip one way or the other. If you put more positive protons on one side and fewer negative electrons on the other side, as far as charges are concerned, and we're not talking about relative masses here, if your brain is going forward, we're just focusing on charges, not masses. But if you have more positive charges than negative charges, what side is going to go down? The positive side. Why? Because you have more positives. Well, what if the opposite is true? If you've got more negatives than you've got positives, which side is going to go down? Well, yeah, the negative side is going to go down. Neutral atoms have the same number of both. Same number of protons as the number of electrons. So when you look at a periodic table, for instance, and you look at the number, the atomic number of one of those elements on the periodic table, and feel free to turn back a couple pages in your book and look at the periodic table now while I'm talking. Find any element on that periodic table and look at it. Find its atomic number. That's the number above the symbol. What does that number represent? It represents the atomic number, which is equal to the number of protons. So looking simply at the atomic number of an element, you know how many protons there are in the nucleus of one atom of that element. Now, using what I've just said about neutral atoms, let's assume that that element has atoms that are neutral. What could you say about the number of electrons? If you look at an element and you find its atomic number is, let's say, 8, we know that there are 8 protons in one atom of that element. How many electrons would there be if it is a neutral atom? That's right, the same number, 8. You could do that with any of the elements. If you assume that you're referring to a neutral atom, the atomic number will tell you the number of protons, positive charges, and it'll also tell you the number of negatives or electrons. Same number of both with a neutral atom. Let that sink in a little bit because that's going to be really important information in just a few moments. In fact, if there's one topic during the whole year that's more important than any other topic, I'd say it's probably this one. Because if you really want to understand chemistry, I want you to really focus on this topic, really pay attention and understand it before you move on. So if you were dozing there just a moment ago when I was explaining the neutral atoms, rewind it a couple minutes and listen to it again before you move on. Okay? Now back to energy levels. Each energy level surrounding the nucleus of an atom has a maximum seating capacity. It has a maximum number of electrons that can fit, just like a sports stadium. And this year in particular, boy, oh boy, if you wanted to buy a ticket for the Super Bowl, let's say, there are fewer tickets available, which means I would imagine the cost is going to be even more outrageous than it normally is, because there are even more limited seats available. And you can't have 2 people sitting in one seat. Think of that analogy as we move forward with the energy levels surrounding the nucleus of an atom. Let me explain. The energy levels are filled from the lower level, which are the inside level, closer to the nucleus, to the higher or the outer energy levels in that order. In that order. Last year, we played a Kerplunk game, if you remember, when we were talking about ecological stability. And we put all the marbles or the balls into the giant Kerplunk game. Which ones were at the bottom layer of that Kerplunk game? The ones that went in first. They were at the lowest level. Which ones were at the highest level of that giant Kerplunk game? The last ones that we put in. Hopefully that makes sense to you, that if you have a container and you fill it with an object or a lot of objects, the objects that go in first are going to be at the bottom. The objects that you put in last are going to be at the top. It is that same principle that applies when we're talking about the energy levels around the nucleus of an atom. If you've got a nucleus, The electrons that gather around that nucleus first are going to be in or found in the lower inside energy levels. The ones that are added to it last will be found in the outer energy levels. And so here's the deal. Each of those energy levels, just like seats in a stadium, there is a limited capacity for holding electrons. Let me show you. Take your time while copying this down. First energy level, again, that is the energy level closest to where the action is, that is closest to the nucleus. The first energy level has only 2 seats available. The maximum number of electrons is 2. Can you have less than 2? Well, just look at hydrogen on the periodic table, and that will answer that question. How many electrons do you think one atom of hydrogen possesses? Find hydrogen. Yeah, do it right now. Turn back, look at the periodic table, find hydrogen in the upper left-hand corner. What is the atomic number of hydrogen? 1. What does that tell you? It tells you the number of protons. So how many protons does hydrogen have? That's right, 1. Now assume it's a neutral atom. How many electrons does it have? Same number, 1. So how many electrons does hydrogen have? 1. And where is that electron going to be? In the first energy level. So in this diagram, in this illustration, only one of these seats would be filled with an electron if we were talking about hydrogen. But most of the elements are bigger than hydrogen, so they have that first energy level filled, and they have second, third energy levels and beyond. This year in 8th grade, we're just going to stick with the first 3 energy levels. I'll let you wait until you get to high school before you learn about the 4th, 5th, and 6th energy levels, because it gets a little bit more complicated, but by then you'll understand it a lot better. The second energy level has a maximum seating capacity of 8 electrons. So in this diagram, the second energy level here, how many seats are available? 1, 2, 3, 4, 5, 6, 7, 8. Second energy level, 8 electrons maximum. Brings us to the third energy level, which also has 8 electrons maximum. And notice the arrangement, 1, 2, 3, 4, 5, 6, 7, 8. And you may wonder if there is any significance to me pairing the electrons in the second and the third energy levels. And the answer is yes, there is significance to it. In fact, I'd like you to develop the habit of pairing the electrons in those energy levels. And when you get to high school chemistry, you'll really understand why that's important. For our purposes in 8th grade here, just pair your electrons. All right. Now let's go beyond this. In the last couple of topics, last 3 topics, we've used this term valence electrons. And I introduced it a few topics ago, but this topic is where this term becomes super duper important. Valence electrons are what determine whether or not and how elements will bond with other elements. So this is a really, really important thing for us to grasp. And if you need to reflect back on previous topics to get this even more, feel free to do so with the videos or the notes in your book. But valence electrons, by way of review, are the number of electrons in the outermost energy level. Now, I emphasize those words for good reason. The valence electrons are not the total number of electrons, only the number of electrons in the outermost energy level that has any electrons in it. So let's look at this picture. In this picture, we've got the nucleus, which contains the protons and the neutrons. Then we have a first energy level and a second energy level. Now, if this diagram is using blue dots to represent electrons, I want you to answer the following questions. How many electrons are in the first energy level? Hopefully you answered 2, and they are right here. 1, 2 electrons in the first energy level. Next question. How many electrons are in the second energy level? Hopefully you answered 5. And here they are. 1, 2, 3, 4, 5. Second energy level. Here's my next question. How many total electrons are there in this diagram? When I said total, hopefully you added them all up. 2 plus 5 equals 7. So there are 7 total electrons here in this diagram. And now for the million-dollar question. How many valence electrons are there in this diagram? I hope you said 5. If you didn't say 5, rewind about 3 minutes and listen to it again. But here are the 5. 1, 2, 3, 4, 5 valence electrons, because that is the number of electrons in the outermost energy level. This particular atom doesn't have any electrons in the third energy level. We don't count 0. The outermost energy level in this diagram is the second energy level. That's the energy level farthest away from the nucleus that has any electrons in it. And how many are in this energy level? 1, 2, 3, 4, 5. That's the answer. Now, before we go any further, I want you to turn back to your periodic table one more time, because I want to ask you some more questions about this diagram. You told me that the total number of electrons in this diagram is 7. How many negative charges are there in this atom if it has 7 electrons? I hope you said 7. Now let's assume this is a neutral atom. If this is a neutral atom, then how many positive protons would there be for this particular atom? If there are 7 negative electrons, how many positive protons would there be? I hope you said 7. That would be correct. Now look on your periodic table of elements from a few pages ago. What element is this a diagram of? Find it on the periodic table. I'll help you out. You're looking for atomic number 7. Atomic number 7 tells you how many protons there are, and if it's a neutral atom, it's also the same number of electrons. So number 7 is nitrogen. Nitrogen. This is a diagram of nitrogen. Okay, we're going to build on that knowledge in just a little while. So let me quiz you here with valence electrons, because it is so vitally important here. Let's go through these valence electrons a little bit more. Here I have a diagram of an atom with no electrons. Here we have the nucleus of the atom, and here we have 3 energy levels. I'm going to show you some different diagrams, and I'm going to ask you questions. I want you to give me the answer. And if you need more time, pause after I give you the question. All right, here's your question. How many total electrons are there? 2 is correct. How many valence electrons are there? 2 is correct. The outermost energy level here is only the first energy level because there are no electrons any further out than that. And there are 2 electrons in that outermost energy level. Next one. What is the total number of electrons here? 6 is the correct answer. How many valence electrons are in this diagram? 4 valence electrons is correct. Remember, valence electrons are those found in the outermost energy level that has any electrons. First energy level has 2. Second energy level has 4. There are no more electrons beyond that. So in the outermost energy level, which is the second energy level in this example, 1, 2, 3, 4 valence electrons. Here's the next. What is the total number of electrons here? 8 is the correct answer. How many, or wait, I'm sorry. Oops. That is not the correct answer. You corrected me. I know. You count better than me. My brain is thinking ahead. Boy, I just gave you a little hint. What is the total number of electrons in this diagram? 10. How many valence electrons are in this diagram? 8. You're correct. Very good. Second energy level is the outermost energy level with any electrons. We've got 2, 4, 6, 8 valence electrons. Let's try this again, and I will try not to give you the answer this time. What is the total number of electrons here? 12. And how many valence electrons are there? Did you say 2? I hope you did. And if you did, you're catching on very quickly. If you're not catching on quite as quickly, review the last couple minutes and watch it again. But 2 valence electrons, I hope you can see why. The outermost energy level here is the third energy level, and there are only 2 electrons there, which is the number of valence electrons. Again, valence electrons are the number of electrons in the outermost energy level. And as we continue with that idea, we have to finish up today's lesson with this idea of stability. Stability on an atomic level in chemistry. And again, this is so vitally important for us to understand. Everything in nature tends to desire a stable state. If you fall off a building, you're not going to be stable until you're dead on the ground. Okay, so don't do that. If you drop a glass off of a table, it's unstable until it falls down to the ground, shatters, and gravity's pulling it down equally. Then it's stable. Might be shattered, but it's stable. Everything in nature strives to achieve a state of stability. And when it comes to chemistry, atoms are stable when their outer energy level is complete, which is why you need to memorize and know what the seating capacity is of each energy level. Because when that outermost energy level is complete, then that atom is stable, like the noble gases. Look at the periodic table again. All of those noble gases are completely stable because their outer energy level is complete. Think of a tower of rocks or a tower of blocks. As you build it higher and higher and higher, it becomes more unstable. It doesn't achieve stability until it actually falls over and it's all level with the ground. This picture here is rather unstable because if you remove one of those rocks, whoo, the whole thing's going to tumble down. But that's kind of a cool picture, I have to admit. All right, so here's the deal. As our concluding point for today, it is the valence number, as I've said before, that determines the possibility and the type of atomic bond. Keep these points in mind throughout the rest of this unit of study. Feel free to watch this lesson over again. But for now, we're going to call it quits, and tomorrow we'll get to atomic bonding. So until then, bye-bye.